Welcome everyone to our lecture series on kinematics. In the last lecture, we covered up till the point of instantaneous velocity. We defined instantaneous velocity. The definition of instantaneous velocity was the rate of change of position of particle per unit time, and we also learned that how do we use average velocity in defining the concept or the notion of instantaneous velocity. The mathematical expression which we use to define velocity v is dx by dt. That is so small change in position of the particle in some small time. Which means that differentiation of the position of the particle with respect to time gives us the velocity of the particle at any given instant. So then we did some example in which we saw that we have to substitute the value of time in the velocity to get the velocity at that instant. For example, if we just look at these examples, velocity at t equal to 1 and t equal to 2. So we had to substitute value of t to get the values of velocity. So that means differentiation is one part of the process, and we have to substitute values of t to get the velocity. And let's proceed further. So this example shows that there is a particle which follows x is equal to at square plus bt plus c, where a, b, and c are non-zero constants. Find the velocity of the particle at t equal to 1 second and t equal to 2 seconds. So how do we achieve that? So first we differentiate the position of the particle. So the velocity would be simply 2at. Differentiation of t square is 2t. We know that the constant remains as is, plus differentiation of bt is b plus 0. So this is the velocity of the particle, 2at plus b. Next, we have to uh, find the velocity of the particle at 1 second and 2 seconds. So we substitute the values of t in what we have obtained. So we have obtained the velocity at any t time to be 2at plus b. So we would substitute the value of t in that particular velocity. So we substitute t equal to 1 seconds here. So that would be 2a into 1 plus b. So that is 2a plus b. Velocity at t equal to 2 seconds would be substituting t equal to 2 in that. That would 2a into 2. That would be 4a plus b. So that is the velocity at t equal to 2 seconds. For velocity, now there is an additional part in this question, that find a condition so that the velocity of the particle is 0 at t equal to 1 and 2 seconds. At 1 second. Solely at 1 second, the particle must have 0 velocity, which means that the particle must stop moving at that particular time. So the question can come in that way also. Now find a condition such that the particle ceases its motion at this time. So when the question says that the particle ceases its motion, it means that the particle stops moving at that instant, or the velocity of the particle becomes 0. So for velocity, 0 velocity at t equal to 1, we put t equal to 1 to be 0, or what we obtain t 2a plus b, the velocity at t equal to 1 to be 0. So this is the condition which we require. Moving ahead, uh, next we have to mark the correct statements among these 4 options. So this is a common uh, uh, idea in objective type questions, that you are given some options, you have to mark a correct statement. And this is the pattern of various engineering examinations, any engineering examination nowadays, which you consider that you have some questions and you have some options, you have to mark the correct options. So not only the subjective approach, but the objective approach in a question is very important. to learn, to deal with whatever examination patterns is going on nowadays and would continue from now on. It's also important to know that the subjective pattern of answering question, that means answering question uh, with different parts, or in a paragraph form. For example, writing one equation, then second and third, and then getting the answer. So the subjective pattern helps the objective pattern. So let's do this question. Our objective is to mark the correct statement. So first option is that the instantaneous velocity of particle is always greater than the average velocity between a time interval. So as per this statement, it says that the instantaneous velocity of particle is always greater than the average velocity. So let's say there is a car which started moving with a velocity of 0 kilometers per hour, and it sped up to some 20 kilometers per hour. Then its average speed would be between some 0 and 20. So we can clearly see that the instantaneous velocity is usually higher than the average velocity. So it is higher when it is at some instant we are considering that at some when the car reached its final speed, then the instantaneous velocity was higher than average velocity. But instantaneous velocity is not always greater. Instant velocity changes. It changed from 0 to 1 to 20. So instantaneous velocity is sometimes less and sometimes more. It's not always greater. So this option is incorrect. For option B, for a non-uniformly or uniformly accelerated motion, the instantaneous velocity of the particle must have been equal to the average velocity within the time interval. So this is actually what we considered in the previous example. Let's say there is a car, and in that car, if we are tracking the speed of the car with time, so the speed of the car is growing with time. So we know that the average velocity must be lying between this point and this point somewhere. It must be somewhere here. This must be the average velocity, somewhere in the middle between the minimum and maximum values of the velocity. So if you can see, this is the minimum value of the velocity 0, and this is the maximum value of the velocity v. The average velocity always lies between those velocities. So when the car is accelerating, it is absolutely clear that it must have been be it must have been at some time have the same value as the average velocity. So what we mean to say is that when the car is accelerating at some instant of time, it must have reached the average velocity and crossed that point. So the instantaneous velocity at some instant must have become the average velocity at some unknown time between the time interval of the motion of the car. So it is pretty clear from this graph. So the instantaneous velocity will become the average velocity at some instant uh, during the overall motion of a car or any kind of motion which you can imagine. Option C, initial velocity of a particle cannot be uh, equal to the final velocity in motion. So this is not a correct statement. For example, we can draw a VT graph, velocity time graph like this. A particle's initial velocity is 0 and final velocity is also 0. Initial and final velocities can be same. So this statement does not make any sense. If a motion in a motion, if the average velocity is negative, then the instantaneous velocity cannot be positive. So this is also incorrect. So let us consider a velocity time graph again. Let's say a particle is moving somewhere like this. So maybe its average velocity is somewhere here. It's negative. It has covered some negative displacement over time. But as you can see that in this particular area, in this particular region, the velocity of the particle is positive. So this statement clearly says that the velocity cannot be positive. So it is an incorrect statement. Velocity of particle can take any values. Now, it's just like saying that if the car is going in forward direction and we are saying that okay, the forward direction is positive, after some time the car went in the negative direction. So overall the displacement of the car is some negative value. Let's assume that okay, it has traveled more in negative than in positive. Then that does not mean that the car would not have ever moved in positive direction. It would have moved in positive direction. Its instantaneous velocity would have been positive, but its average velocity over the total time interval is negative. So this is what this option meant. The position of an object. Let's jump to the unsolved questions. Moving along x-axis is given by x is equal to a plus bt square, where a is equal to 8.5 meters, b is equal to 2.5 meter per second square. What is its velocity at t equal to 0 and t equal to 2 seconds? And what is the average velocity between 2 seconds and 4 seconds? So to find the velocity, we mean to find the instantaneous velocity. So first, let us differentiate the velocity. To get the velocity, so we differentiate the position. So dx by dt, that is d by dt of the position of particle, that is a plus bt square. So d by dt of a is 0 plus d by dt of bt square is 2b into t. At t equal to 2 seconds, we substitute the value of t. The velocity of the particle at 2 seconds, so would be 2b into 2, that would be 4b. Now we can use the value of b which is given to the question, which is given 2.5. 2.5 times 4 is 10. So that means the velocity of the particle at 2 seconds is 10 meter per second. Similarly, the velocity of the particle at 1 second, at 0 seconds, would be 0. At 0 seconds, if you put value of 0, this is 0. Now we have to find the average velocity between 2 and 4 seconds. That means we have to write the equation of final position of the particle. Yep, the final position of the particle. So the final position of the particle is some at t equal to 4 seconds, right? So that would be a plus 4 into 4 substituted over here would give us 16b. The initial position xi is a plus 4b. The displacement is 12b. The time interval is 2 seconds. That means the average velocity is 12b upon 2, that is 6b. This is v average, can be written like this also. So this is v average, and 6 times 2.5 is 15 meters per second. So this page is a repeat of last one. Okay, now coming to the second question. The relation between t and distance x traveled by a particle, or the position, this should be the position. The relation between time and position is t is equal to ax square plus bx, where a and b are some constants. You have to find the velocity of the particle in terms of x. So in the previous questions, what we did was that okay, we had x is equal to some a t square plus bt plus c. So we straight up differentiated the position of the particle with respect to t and got the velocity of the particle in terms of t. Since x was in terms of t, we found the velocity in terms of time, and then we substitute values of time to get on with our question. So here, that value of time is given in terms of x. So what should be our approach to get the velocity? So instead of differentiating position with respect to time, here we can differentiate time with respect to position. That means we can do is that we can write dt by dx. That means differentiating t with respect to x. Now the variable here is x, so it would be easier to differentiate in terms of x. So differentiating with x, we would get ax squared differentiated would give us 2ax. Differentiate of bx would give us b. dt by dx. So how do we write dt by dx? So you can easily imagine that dt by dx is nothing but 1 upon dx by dt. If we reverse dx by dt, it is dt by dx. So that means dt by dx is nothing but 1 upon v. Or v is equal to 1 upon 2ax plus b, which is option D. X is equal to t cube. Find the velocity of the particle at t time, where the time where we are looking for is t equal to root 3 seconds. So here we simply differentiate the value of x. So when we differentiate x, we would get velocity is equal to some 3t square, and we put root 3 over here, so we would get 3 into 3, that would be some 9 meters per second. A particle follows the equation x is equal to a sine omega t. Find the velocity of the particle at t time, at t equal to 0, at t equal to pi by 6 omega, at t equal to pi by 3 omega, and t equal to pi by 2 omega. So at different time intervals, we want to get the value of the velocity of the particle. So the velocity of the particle is some, when we differentiate a sine omega t, we can write it as d by dt of x, which is a sine omega t. So how do we differentiate a sine omega t? So we know that the term outside the sine function would remain as is. That means the term which is multiplied with the thing which is varying just comes outside. So the term a would come outside since it's a constant. Differentiation of sine omega t. When sine omega t is differentiated, we get cos omega t, and differentiation of omega t is simply omega. So that is what we learned in differentiation, that if you have a term, a constant in the argument of the function, then that particular constant comes outside. So here the constant in the argument of the function was omega t, that was the angle. So the constant in the angle omega, it came outside and it became like this. So this is some a omega cos omega t. So this is the velocity of the particle at some t time. Now just let us substitute values of t and get the velocities at different time, and just we'll write it over here. Velocity at t is equal to 0, cos 0 is 1, so that would be a omega. Uh, at pi by 6 omega, so when we put pi by 6 omega over here, so that would be cos pi by 6, so that would be uh, root 3 by 2, so that would be a omega root 3 upon 2. Similarly, substituting value of pi by 3 omega, you would get a omega by 2. And the last part is left for you as an exercise, that try to find the value of velocity at this particular time by substituting this time in the velocity which we have obtained. Okay, next we proceed further. We try to write the value of average acceleration, or we try to study what is average acceleration. So in average acceleration, we learn a simple definition that average acceleration of a particle between some initial and some final point is some final velocity minus the initial velocity of the particle divided by the time interval of the whole motion. So that means that we are studying the rate of change of position of the velocity of the particle with respect to time. So the definition, in fact, resembles rhymes like that only. It resembles the definition of velocity where we said that the rate of change of position of the particle with respect to time. Here we say that velocity, the rate of change of velocity of the particle per unit time is average acceleration. So it is defined as some final velocity minus some initial velocity divided by the time interval in which the change has taken place. So this gives you an overall idea that how the velocity is changing, how fast the velocity is changing, and it is pretty important to judge. For example, uh, let's say if we release a ball over some height, then how fast that ball gains some speed would represent that what is the value of action to gravity at that planet. So if action to gravity is high, then it would gain more speed as it is falling down in that time interval. So average acceleration, the expression for it is simply the final velocity minus the initial velocity divided by the time interval in which the change has taken place. So average acceleration would have what units? Let's say we want to study the units of acceleration. Then the numerator is meters per second, and the denominator is simply 1 second. So that would be 1 meter per second square. Um, Now let us come back to instantaneous velocity. So when we were defining instantaneous velocity for a single dimension, we said that the velocity is some dx by dt. Now take a simple example. Let's say you have a curved surface like this. There's a curved surface, and over that surface you have some kind of block which is moving. And let's say this direction is x, and let's say this direction is y. Then we can imagine that the velocity of the block in x direction and y direction would be some different values. So this is a case of motion of a block in two directions, or the velocity when the velocity of some particle is in two directions. So how do we define it? So the definition is same as what we have learned already. The definition is velocity in x direction is some dx by dt, and velocity in y direction is some dy by dt. One more way of studying instantaneous velocity is imagining, let's say we have a particle which is moving in a circle. So the particle, when it is going in a circle, may have some velocity in, let's say, some y direction at some instant, and opposite to x direction at some other instant. So that means velocity of the particle is constantly changing along different directions. Not only it is present in different directions, it is also changing. So how do we define it? The definition is simple. Velocities in x direction is represented as vx. Velocity in y direction is written as vy. Vx is equal to the differentiation of x with respect to time. and velocity in y direction is differentiation of y with respect to time. And this is what they signify, that Vx signifies that how fast the position of the particle is changing in x direction, or dy by dt signifies how fast the position of the particle is changing in y direction with respect to time. If we want to write the velocity of particle as a vector, we write Vx I cap plus some Vy j cap. So this becomes the velocity vector. Just like we wrote the position vector, where we wrote some xi cap plus yj cap. So instead of x and y, we are writing Vx and Vy. So we can even say that the velocity of the particle is some dr by dt, that is differentiation of position of the particle with respect to time, is the velocity. So this is an important expression. Now here we are mentioning that case, since the x and y coordinate of the particle are mostly independent of each other, similarly the velocities in x and y direction are independent of each other. Let us take an example. A particle moves in accordance to the law x equal to t and y equal to t square. So what this line means is that the position of particle at some t time is represented by this expression, and the position of the particle at some t time in y coordinate is represented by t square. So we can differentiate them separately. So we differentiate the position of the particle with respect to t. So when we differentiate that with respect to t, we get Vx is equal to some. First, we write the expression Vx is equal to dx by dt, and Vy is equal to some dy by dt. Differentiating x with respect to t, we get Vx is equal to 1 meter per second, and Vy is equal to 2t meter per second, since differentiation of t square with respect to t is 2t. Then we write the whole uh, the expression which we have obtained, the answers which we have obtained in terms of vector. So we write velocity vector as some velocity in x direction, which is simply 1 I cap, plus velocity in y direction, that is 2t and j cap. So that means that extending velocity of a particle in one dimension to two dimension is pretty simple and straightforward. We differentiated the velocity of the particle with respect to time, and we got the velocities of the particle at some t time, and then we substituted values of t to get those velocities at those times. So the same case happens in the two-dimensional case also. We are substituting differentiating velocity, we are differentiating the position of the particle, x coordinate and y coordinate, and getting the velocity in x direction and y direction separately. And as you can see that they are mostly independent of each other. So now let us proceed further, that how do we apply this again. Now instantaneous speed is defined in this example. So this example serves as a definition for us, that the instantaneous simply of a particle is simply the magnitude of its velocity, that is the magnitude of this velocity vector. And that's why it was important to understand that velocity is a vector. The velocity vector is some Vx I cap plus Vy j cap. So the magnitude of that velocity, whatever that velocity may be, would be the speed of the particle or the instantaneous speed. So this is instantaneous speed, or the expression for instantaneous speed is the velocity vector's magnitude. Okay. The coordinates of a moving particle at any t time are given by x is equal to alpha t cube and y equal to beta t cube. You have to find the speed of the particle at t time. So we would try to find Vx. What is Vx? Vx is differentiation of this term, which would come out to be some 3 alpha t square. Differentiation of beta t cube. So beta remains as is. And differentiation of t cube we get again t square. So how do we get the magnitude of velocity? So the magnitude of any vector is the square root x component of that vector, that is vx squared, plus y component of that vector squared. So the x and y components in a velocity vector are vx and vy. So those are squared and added and taken a root. So this gives you the speed of the particle. So after substituting these values in this expression, we would get 3 t square square root alpha square plus beta square. And that would be the speed of the particle at any t time. Now let's say a particle moves as per x equal to t square. Find the average acceleration of the particle between 0 second and 1 second. So to find the average acceleration, we have to find the final velocity minus some initial velocity divided by the time interval. So we have to differentiate x equal to t square, that is 2t. Velocity and t equal to 1 seconds would be the final velocity. So we put t equal to 1 here, so that would be 2 minus the velocity at 0 seconds. We substitute value of 0 over here, that would be 0 divided by the time interval, which is 1 second. So the average acceleration becomes simply 2 meter per second square. Okay, so after defining average acceleration, now we have to define the instantaneous acceleration of a particle. So uh, now let us come back again to the example of a, let's say, moving car. So when the car is starting from its rest initial position, so the car may have some high acceleration. So as you apply pressure on the accelerator pedal of the car can speed up in a faster way. So how far we have pushed the accelerator pedal determines how much fuel is being injected in the engine of the car, or how fast the car is gaining the speed. Um, again, one more case can be, let's say you can take an incline. The incline is something like this, and let's say you put a block over that incline. So this is a block, and we place this block on this incline, let's say. So let's just make a block like this. Now let us take one more incline, and we drew an identical block like this. Now both the inclines are smooth. So on which surface do we expect that the block would gain speed in a faster way? So that is the question. Let's say we have incline A and you have an incline B. So on which incline would the block gain speed uh, faster? So the obvious answer would be A, because it is more slant. It is more steep incline. So on a steeper incline, when a block is placed, it would gain speed in a faster fashion. So what was the difference? What was the physical quantity which was different between these two situations? So that physical quantity is the acceleration. That how fast your speed is changing, how fast the velocity of the particle is changing. So for one dimension, the acceleration of particle is defined as the rate of change of velocity at an instant. So it is defined in the same way. We say that the instantaneous velocity is defined as dx by dt. So the instantaneous acceleration is defined as the differentiation of velocity with respect to time. So the acceleration is some dv by dt. And for two dimensions, the same story can be repeated, that the acceleration of particle is differentiation of velocity of the particle in x direction, and differentiation of the velocity of the particle in y direction. So the complete acceleration in two dimension becomes differentiation of velocity in x direction with respect to time, I cap, plus differentiation of velocity in y direction with respect to time, and some j cap. So this becomes the complete acceleration vector of the particle. So similarly, acceleration of particle can also be written in average acceleration can be written in vector form. We can just simply put the arrowheads over the top of the velocity vectors. That is final velocity. This is the final velocity, and this is the initial one. The final velocity minus initial velocity divided by the time interval is the average acceleration of the particle, except that now it is a vector. So this is what acceleration was about. Just recapping what we have done. The acceleration of particle, let's say when we're defining for one dimension, is defined as the rate of change of particle, rate of change of velocity of the particle per unit time at a certain instant. Whereas in average acceleration, it was the average rate of change. That is how fast the change has happened over an interval of time. In instantaneous acceleration, we want to say that okay, how much the accelerator pedal is pressed at right at now, at this instant, uh, how much fast the car is accelerating, how much fast the velocity is changing at a single instant. Then that becomes instantaneous acceleration or simply acceleration, and is defined as the differentiation of velocity with respect to time. For two dimension, we say that we have to differentiate the velocities in x and y direction, just like we defined for velocity. For velocity, we said that you have to differentiate the velocity, differentiate the position of the particle with respect to time, the x position of the particle, put an I cap, plus the differentiate the y coordinate of the particle with respect to time, put a j cap, and that whole vector becomes the velocity vector. In the same way, the acceleration vector is also defined. So let us now jump on to some questions. So let us take an example. We have to write the average acceleration, the instantaneous acceleration of the particle, which is having velocities in x and y direction like this. So the velocity of particle in x direction is equal to t. The velocity of particle in y direction is equal to sine omega t, and omega is some constant. So what is the acceleration? So we differentiate the velocity of the particle with respect to t, we get a 1, and we differentiate the y directional velocity with respect to time. The sine omega t is differentiated as cos omega t, and the coefficient in the angle of the functions comes outside, that is omega cos omega t. So this we already know, we have already done it. So the acceleration of a particle is some I cap plus omega cos omega t j cap. The acceleration can also be written in terms of position of the particle. So one good way of finding the acceleration is to remember these expressions. So these expressions are very important when the acceleration of particle, velocity of the particle is non-uniform, or the acceleration is non-uniform, and acceleration is expressed in terms of x. So we differentiate the velocity in terms of x or with respect to x as is given in this expression, and then we multiply the velocity with the differentiated part, and we get the acceleration in terms of x. So this is vx dvx by dx. So this would be acceleration in x direction, and this is v by dvy upon dy, and this would be acceleration in y direction. So let us take an example. We are asked to see that there is an expression t equal to ax square plus bx. Find the acceleration in terms of x. So this is a part which we did earlier, that we found the velocity for this kind of expression, which was 1 upon 2ax plus b. Now we have to proceed further from that part. We have to find the acceleration of the particle now. So the acceleration of the particle, we know that we have to differentiate with respect to whatever variable is given in the question. So that is x. So we differentiate this with respect to x. So once we use the quotient rule, we would get dv by dx is equal to minus 2a. So if you remember, this is the constant with x, so that just comes like this, and this is 1 upon 2ax plus b square. Acceleration is v dv by dx. So what we are doing here is that we now multiply the velocity with what we have differentiated. So the velocity is 1 upon 2ax plus b, and what we have differentiated is minus 2a upon 2ax plus b square. So combining these two expressions, we get minus 2a upon 2ax plus b cube. Now 1 upon 2x plus b is velocity, and this comes 3 times over here. So this would be acceleration is equal to minus 2a v cube. So this is a very neat expression which we can obtain eventually, but our objective was to find the acceleration in terms of x, which is this minus 2 upon 2x plus b cube. Now particle moves as per x equal to t star plus t. Find the velocity of the particle and acceleration of the particle at some t time. So we differentiated the velocity of the particle with respect to time to get acceleration. Here we are given the position. So first we find the velocity of the particle. The velocity is some d by dt of x, that is t square plus t. So that would be some 2t plus 1. Again differentiating velocity with respect to time, we get 2, differentiation of t would be 1 plus 0. So that would be simply 2 meter per second square. A particle follows x is equal to t square. Which option is r correct? So the displacement of the particle in a second is proportional to n. So for these kinds of expression, when x is equal to t square, uh, let us try to find what is the displacement in nth second. That is, what is the position particle in n plus 1? That would be n plus 1 whole square minus position of particle in n seconds. That would be simply n square. So when we are asked that what is the displacement of the particle in nth second of motion, we are basically asked what is the difference of these two things. That what is the change in position of particle between n second and the consecutive time interval of 1 second. So that displacement delta x is n plus 1 whole square minus n square. So that would be simply 2n plus 1. So as you can see from this expression, the displacement of the particle is proportional to n. So this option is correct. Next, it is given that the acceleration of the particle is constant. So we differentiate this twice, you would get a constant. So this would also be correct. The velocity of the particle is constant. This is absolutely incorrect, since the velocity of the particle at t equal to half second is 1. So when you do that, this option would also be come out to be correct. So moving on. So to further apply the ideas which we have learned over here, majorly what we have learned is that the acceleration is some dv by dt, and when two dimensions are given, then acceleration is some dvx by dt, and acceleration y direction is some dvy by dt. And acceleration can be a constant and can be a variable. For example, in this case, acceleration is clearly a variable. It depends upon x, so it's a variable. In this question, the acceleration is a constant. even in the further questions, acceleration is sometimes constant and sometimes it's not a constant. So it's not a given that acceleration is always a constant. It's just that the questions in which acceleration is constant are asked much more times, and it then itself becomes a whole complete topic, that what is uniformly accelerated motion or motion of a particle in uniformly accelerated conditions. So when we talk about uniform acceleration, so when we are talking about uniform acceleration, we are talking about acceleration of particle is some constant, and since it's a constant, the situation is pretty easier to deal with, and we have some set of equations which you already know to deal with those situations. But what if the acceleration of particle is not a constant? So in those cases, we come back to our fundamentals that acceleration is some dv by dt or acceleration some v dv by dx and proceed from that. So to proceed further, we want to learn a bit more about a new mathematical tool which is related to what we learned earlier, which was differentiation, and that tool is integration. So let's start with this. So integration, first we would do indefinite integration. So indefinite integration is the inverse process of differentiation. So for example, if we differentiated something and we got, let's say, something called cos x. For example, we know this much only, dy by dx was cos x. Then we would say that, okay, when we would integrate cos x, we would get sin x. So this is what written here. We put an integral sign, which is something like this, an elongated sign. We put cos x over here. We put an element dx, the thing with respect to which we want to integrate, and then we integrate it. So when we differentiate sin x, so we got cos x. So when we integrate cos x, we have to get sin x. So this is the idea behind integration, that it's just an inverse process, the inverse process of differentiation. Now we put a constant with it. So we put a constant so that we do not know what cos x came from. For example, it is given to us that the dy by dx was cos x. So when we integrated, it could have been sin x plus 2 also. For example, if I differentiate sin x plus 2, differentiation of 2 would be 0 and it would come out to be cos x. So how do I know that there was no 2 or there was 2000 in its place or it was some 2.5? I do not know what constant that was. So we put an arbitrary constant over here. This is an arbitrary constant which is called the constant of integration. So after integrating anything, we put a constant with it, which is called the constant of integration, and then we proceed. For example, there's a constant. We have to integrate a constant. That constant simply comes outside of the integral, and we then integrate. So now some common formulas of integration are given. So one of those formulas can be integral x dx. So integral x dx is x squared by 2. So if we differentiate x squared by 2, you would get x. So that is the purpose of what we are doing. That if we differentiate x squared by 2, we must get x. If we differentiate cos x, we must get sin x. So there is a negative sign there. Differentiating this term would give you this term. So these are all expressions which should be requiring to learn. So this expression x ki power n dx, these are the expressions which we need to focus on. Integral of x dx, this is some x square by 2. Integration of sine x, this is some minus cos x. So these are the important terms which we have to remember essentially. Integration of x ki power n. So if we remember differentiation of x ki power n, it was n x ki power n minus 1. Integration of x ki power n, x ki power n plus 1 upon n plus 1 plus some c. So this would be a new expression. Differentiation of ln x was 1 upon x. So that means differentiation of 1 upon x would be ln x. And these are the further expressions which would be used further. Next, we jump on to definite integration. So definite integration is where integration comes in its application. What is its application when we talk about it? So basically, y and x, when we draw a curve, sometimes we want to find the area behind the curve. So that is what is written here. If you would see, for a y-axis curve, the definite integration is used to determine either an integral or an area. So integral y dx, and we put some values a and b over here. So this represents the area within the curve and the lines x equal to a and x equal to b. So this is what is meant by definite integration. It shows you this complete area, this complete area, this. So this complete area would show us would be obtained by calculating this integral. So how do we calculate this integral? That will continue in the next lecture. So thank you for watching.